Hello, I'd like to show you my bike lights. These LEDs go all the way around the rim, and when it's spinning, it looks like this. This is a mess, but if we switch modes, we get this. In this video, I'm going to explain how these work, but first, let's kill the lights. So those are the lights, and I will go into how they work, but first, a bit of a backstory. A few years ago, I did a bike light project on this same bike, where I put a couple hundred LEDs onto its wheels. This was done with 2 battery-powered LED strips per wheel. The lights were bright, and the bike was very safe to ride. Cars gave me plenty of room when riding, but it had problems. First off, power. Each strip used 3 AA batteries. I was not into the idea of trashing a dozen batteries at a time after a few rides. And they're heavy. Weight is a bad thing when you're spinning it around. Next up, control. Let's look at the buttons here. Mode, speed, and color. So changing the light setup was a lot of presses on these buttons. And if you hit it one time too many, you go all the way around again. This was bad enough for 1 strip, but for 4, it would take a long time between setups. But the biggest problem of all for me was that the lights were boring. Each strip can only show 1 color at a time. That's just illumination. As you know, LEDs are way more exciting than that. We can use them to display all kinds of patterns. Even a simple color cycling effect makes a gaming PC or workspace look way better. The problem is the wheel movement. Like we saw earlier, any pattern gets messed up by spinning it around. When these wheels hit 14 miles per hour, they're doing 3 full rotations per second. So that leads into the big idea for this project. If I know the speed that the wheel is spinning forwards, then I can move the animation backwards at something close to the same speed so that the result is that the visuals are moving forwards slowly. That way I can put lots of different patterns onto the wheels and have them still be clear and visible. So there's the first problem, getting the speed of the wheel. One way to know the speed of the wheel is how bike speedometers have been doing it for a long time. I'm using one right here for testing the wheel. You put a magnet on the wheel, and you have a sensor on the fork to sense when the magnet passes by. This way, the speedometer can get the seconds per revolution and convert that to miles per hour. There are 2 big problems with this system. When you're riding slowly, there's a 1 rotation delay for updating the speed, and it looks sloppy. The other problem is when you're riding along and hit the brakes quickly. The lights seem to glitch out, and it breaks the illusion. So this system won't work out for the lights. I also tried using my phone's GPS, but that was way worse. It's laggy and low frequency, leading to big jumps in speeds. The solution comes in the form of this itty-bitty gyroscope sensor. The same thing that is used in smartphones to detect if they're rotating or twisting for gesture control. You can see these readings in this app. Here's movement on the x-axis, the y-axis, and the z-axis. Even better, it can update those readings at 100 times per second. So if we use that to determine the light animation, we can get something that is very smooth. So even if I give the wheel a hard shove or quickly bring it to a stop, the animation can remain stable. All this leads to my original goal for this project. This is pretty pathetic, but in the beginning, it's all I wanted to do. I just wanted to show that I could make this smooth and let other people go from there to make it nicer. But then the pandemic kept going, and I needed to make this more interesting. So I ran into the second problem, how to add patterns. And wait, before that, let me quickly go through how these LEDs work. These LEDs have a controller that is sending it new colors several times a second. And here's what happens if I pull out this wire. I can play with it a bit. What's important is that these lights will hold on to a color until they get a new color to display. What the controller is doing is sending out a new set of colors for all of the LEDs for each frame of animation. How this works is pretty cool. Each LED chip grabs the first color in the data stream and then passes the rest along to the next LED. But what is a color? Each LED defines color in the same way that we define color on a screen. We have 256 values, 0 to 255, for each of the component colors, red, green, and blue. It's not exactly the same. I'm ignoring gamma and temporal dithering, but that's another topic for another time, and this is good enough for now. The main thing here is that we need a 0 to 255 value for each color for each LED. If a bike wheel has 100 LEDs, I need arrays of 100 colors each. But that's a lousy system with no flexibility, and it's painful to look at in terms of code. If I wanted to change the look of a pattern, There are lots of values that need to be edited. But the bigger point is that it's not scalable. What if I wanted to add one more LED? Or make this smaller for a 20-inch wheel with about 80 LEDs? Or a bigger wheel? I'd have to be editing lots of numbers to make this fit again. The solution is in the Fast LED library with palettes. These work like gradients do with CSS on the website. And if you don't know what that means, you have one color on one side, another color on the other side, and the computer calculates all the values in between. For our system, all we have to do is include a location value along with the RGB values. If we have a pattern where we want a hard edge of two colors, we can place two colors right next to each other. This solves for scalability, but not entirely for readability. Here's what this pattern and its code looks like. This is one of the few patterns that I created by hand. This was painful. So I made a web app to fix this. Here I can add and edit colors. They can be solid colors or gradients. I can also repeat patterns and add gaps between each group. And I can spin it. Then I just copy what's in here and push it to the Arduino. Now it's easy to make new patterns based on flags, logos, and even this shirt. And with that, I was truly done with the project. I can send anyone that link and they can make their own patterns. You can try it right now. It's in the description. And that didn't last as long as I'd hoped. I like the patterns, but I wanted something more dynamic. I already had some static fireball patterns, but now I wanted a dynamic, animated fireball. I could have gone with a set animation that looped like an animated GIF, but then there's the whole scaling problem again. So I went with a particle system. Particle systems are used all the time in video games for explosions or dust. Instead of 3D objects, these are huge arrays of points in space, dots, that some image will be attached to. Let's look at a particle system in 2D in its raw form. Here we see a bunch of dots coming out from where the mouse is. The mouse is effectively the origin, or the emitter, for all of the particles. And here it is with shapes attached. For my wheel, I'm only working in 1D, a line. For this fireball, there are 1 or 2 emitters that stay in place with particles flying away from them. The sparks work as bursts, where the emitter is only there the moment they start. Oh, and the batteries. I replaced those 6 AA's with 1 rechargeable. I can use 2 for a longer runtime if I want. If you do ride and don't have any lights at all, please check these out. You can get a set of bright lights front and back for $20 and they're rechargeable by USB. So worth it. And lastly, when not moving, the wheels do this. This is a noise algorithm and is covered by one of my earlier videos. Thanks for watching. Please like and subscribe for my occasional videos.